Differentiation Mobile, quality e-learning experience on the go.
Hello and welcome back to the class. I want to believe that you must have done the necessary revisions and practices with the above given laws of differentiation, and henceforth we'll kick off into learning some other aspects of differentiation. And the first aspect I want us to talk about today is called functions of function. Differentiation. Okay, we'll be talking of functions of a function. Okay, functions of a function. Alright, functions of a functions normally occurs in a derivative. Here you have going to explain that, assuming we are given that y is equal to sine of 2x minus 3. Okay, this is a function of a function. Okay, or let me use two examples to explain this. y is equal to 3x plus 3 raised to power 4. This is a function of a function. The first function here is a function of two functions, where you have a linear function 2x minus 3, a linear function. Okay, and then you have sine of this, okay, sine of the linear function. Okay, this one is a trigonometric function, a trig function. Alright, and then in question number 2 you have 3x plus 3 inside the bracket, which is a linear function too. Okay, and then you have also that 3x, assuming it is a, okay, raised to power 4. Okay, this is an index function. Okay, I hope you now understand what we mean by it. Functions of a function, functions that have two functions and one, they can as well have three. Okay, but for our study will be limited into having two functions and one. Alright, we will be given steps on how you resolve functions like this using the following solution. Solution for 1, y is given as sine 2x minus 3. Okay, the first thing you have to do is to denote one function. You can say let 2x minus 3 be equal to u, so that y will be equal to sine of u. Okay, fine. So remember that u is equal to 2x minus 3. Alright, how this really works out is that you will have to differentiate y with respect to u, and when you differentiate a sine function, alright, you will have cos of u. Okay, from our table we said that when you differentiate sine x is equal to cos x, so if it is sine u, it is equal to cos u, and so that's why we have cos of u. And so we go back and differentiate u with respect to x, and now we'll go back and differentiate u with respect to x, and u is given us du dx will equal to, when we apply our binomial function x and x raised to power n minus 1, do that carefully. If you differentiate 2x, you will have 2, and if you differentiate minus 3, you have 0, because it's a constant. Okay, so what we do next is to multiply the two outcomes, cos u and 2u. Why do we really multiply? Because when we multiply du du by du dx, okay, the u will cancel out the u, giving us what? Dy dx. And so since we are multiplying the other side of the equation to get dy dx, okay, we will have to multiply this other side of the equation to get the outcome that follows dy dx. So I have 2 times cos of u, okay, which will give us 2 cos u. Alright, so we can say dy dx is equal to 2 cos u. And what is u? Where u is equal to 2x minus 3, and so we can say this is 2 cos of 2x minus 3. Alright, so this is the dy dx of that function. And so we'll go back and do for solution 2. You'll have 3x plus 3 raised to the power 4, and if y is equal to 3x plus 3 raised to the power 4. Alright, so all we have to do here is to denote 2. We can say let u be equal to 3x plus 3. It may not really be u all the time. You can use any alphabet, letters of the alphabet to represent here. So my new y is equal to u raised to the power 4. I can differentiate y with respect to u to be equal to 4u cube, okay, using first principles, and then I can differentiate u with respect to x to give me 3. Differentiation of a constant is 0. Alright, so that du dy du times du dx, okay, which will eventually give me dy dx will be equal to 4u cube times 3, okay, and 3 times 4 gives 12, okay, 12u cube. Fine. And then where my u is equal to 3x plus 3 all cube. Okay, I just carry back my u into my final outcome. Alright, so this is how you work on functions of a function using derivatives. We'll go ahead and then talk of the quotient rule. We have previously stated the quotient rule and the product rule, so we have to apply them. Alright, product rule. Okay, product rule is used when two functions multiply each other. Okay, that is why, assuming y is equal to u times v, okay, a function u and a function v, and dy dx will be equal to v, you keep v constant, then you differentiate u, and then you keep u constant, and then you differentiate v. Fine. So we'll try to apply this to 2 examples too and see how this really works out. Alright, so assuming y, for example, okay, example number 1, maybe we are told to differentiate a y equal to x raised to power 3 sine x, okay, and then you're given another function. I want to get another function different from this, and then b, maybe you're told to differentiate exponential 5x and 4x squared. Alright, you see these two are different functions. These two are different functions too. Alright, so the first thing we do is we denote them as u's and v's. Here to u's and v. Alright, solution A. Here you have the y is equal to x cubed sine x, okay, and we know that from this point, okay, we can now write that dy dx is equal to, the instruction says we keep v constant. This is my u and this is my v. Keeping v constant, I have sine x, and then differentiate u, okay, u is x cubed with respect to x, okay, and then an addition sign follows. Keep u constant. This is my u and then differentiate v. V is sine x, okay, and then dx. Alright, and so dy dx will be equal to have sine x here. If I just differentiate x raised to power 3 using my binomial method, I have 3x squared, okay, and then from this point I have x cubed 2, and if I differentiate sine x, I'll have cos x. Check your table, and so this gives me 3x squared sine x plus x squared s cube cos x. Fine. Some things are common, some things can be bracketed, but at this point your examiner gives you the hallmark, but you can as well group some into brackets if you want to simplify them more. You find out that s squared is common between the two brackets, so you can say that this is dy dx is equal to x squared into 3. We'll be left with 3 sine x here, 3 sine x plus, and for this we'll be left with x cos x, x cos x, and so this becomes the final outcome for this computation. This becomes the final outcome for this computation, and so we go over and solve for the second expression. Check for the second solution, solution B. Solution B, and in solution B we have we are given exponential raised to power 5 times 4x squared, exponential raised to power 5x times 4x squared. And so here we denote this as u, and here we denote this as v, and then we'll carry out the normal dy dx, which is equal to v du dx plus u dv dx, okay, which implies that we have keeping v constant, we have 4x squared, and then du dx is differentiating exponential 5x, okay, with respect to x, okay, and then we have plus u, we keep exponential 5x constant, and then we differentiate 4x squared with respect to dx. Alright, so in the next slide we have 4x squared differentiating exponential 5x. We'll have to do that in the next page if you want to find dy dx of exponential 5x. Okay, if y is equal to exponential 5x and you want to find dy dx, alright, you have to note that exponential 5x is a combination of two functions, and so we say let 5x be equal to u, alright, so that we have y to be equal to exponential u, and then dy du is equal to exponential u, alright, and then dx, sorry, du dx is equal to 5. You know, we said that u is equal to 5x. Alright, and so we can multiply the two functions by saying that therefore dy du times du dx, okay, which is equal to dy dx got 5 times exponential u. Alright, and we have 5 exponential u, exponential u is equal to 5x, and so we pick that and then put it here, 5 exponential 5x as derivative here, plus exponential 5x, and then when we differentiate 4x squared we'll have 8x. Alright, so you can write this as 4x squared, 4 times 5 is 20, and then we have 20x exponential 5x, and then plus we have 8x then exponential 5x. Okay, and then we have something in common here between the two brackets. X is common, and 2 is common between 8 and 20, and so we can say that, and 4 is also common for x bracket 5 exponential 5x plus we have on this part 2x 2 exponential 5x. Alright, and so we can write this as 4x in the bracket of 5 plus 2 gives 7 exponential 5x. Alright, so this becomes the outcome for differentiating these two functions. And lastly, we'll be considering the quotient rule, and then we'll be solving it all together. We'll be solving using just one example because it's a tedious method. And okay, let's do for two examples too. Quotient rule. Alright, quotient rule are used when functions divide each other. Used when two functions divide each other. Alright, and if we want to use quotient rule, then you should have that y is equal to u over v, and then the x is given as is given as v, du dx minus u dv dx all over v squared. Okay, all over v squared. And so we should take two examples. Number one example 1, you have to differentiate the following functions. And A, you are given let me find some other function. I think that will make sense for us to understand. Alright, A, you're given y equal to 3 squared over cos x. Okay, given y equal to 3x squared over cos x, and then B, you are given that y is equal to sin x all over cos x. Fine, so work with this. Solution A, okay, given the expression above, we can say that dy dx is equal to v du, where we have this as u and v, the numerators as u and the denominators as v. Alright, and so we have from A that we keep v constant and v is cos x, and then we differentiate u, which is 3x squared, okay, with respect to x, and then we subtract and keep u constant 3x squared, and then we differentiate cos x with respect to x, and then the denominator becomes v squared, where we have cos x all squared. Alright, this will be equal to cos x. When you differentiate 3x, you have 6x minus 3x squared. Okay, and when you differentiate cos x, you have minus sin x. Fine, and then the numerator becomes cos squared x or cos x all squared. And so we'll go for the next slide. We'll have the dy dx is equal to 6 cos x, start 6x cos x rather. Alright, plus, because the two minus sign will multiply each other, and then we'll have 3x squared sine x. Alright, all over v. Okay, v squared is given as cos squared x, cos squared x. Alright, we have some things to factor here. We can factor 3x, so that here becomes cos x, 2 cos x, okay, plus then we'll have x sine x, then all over cos squared x. Right, you can simplify further by saying let this becomes 3x okay, 2 cos x. I think once you've gotten to this point, you have arrived at the most important outcome. Okay, every other thing you can do is to simplify to get the outcomes easier. Alright, and so the second question says that y is equal to sine x all over cos x. Alright, and I want us to remember that sine x over cos x is equal to tan x from your trigonometric ratios. Okay, this property holds. So a good way of doing for tan x is using this, and so this can also be tan x. Alright, we'll find y dx to be equal to u dv, v du. We have keeping v constant, and then we differentiate u. Okay, this is my u and my v with respect to x. Okay, plus keeping u constant, and then differentiating v. That's minus, not plus, with respect to the x. Alright, and then all divided by v squared. V squared is cos squared x. Alright, still the same mistake. Alright, and so all we have to do is for the next slide we have that dy dx is equal to cos x. When we differentiate sine x, we have cos x, to have cos x, and then cos x, and then minus. When we have sine x. When we differentiate cos x, we have minus sine x. You can check your table of sine x, and then minus sine x all over cos squared x. Okay, and this is equal to cos squared x plus sine squared x. Okay, because the minus changes to plus all over cos squared x. But you're told in trigonometry that cos x plus sine x is equal to 1, and so this gives us 1 over cos squared x. Okay, and also from your trig, you're told that 1 over cos x is equal to sec x. Alright, so you can write this as 1 over cos x, okay, all squared. You can write this as 1 over cos x all squared, which is equal to sec x all squared. Okay, which is equal to sec squared x. That's why when you go to your table, you see that we said that when you differentiate tan theta, it gives you sec squared x. Alright, I think with this we've come to the end of this class, and the next thing I want to talk about is differentiation of exponentials. Before we close, this just came to my mind: differentiation of exponentials. Okay, we've done this before we met this in one of the derivatives we treated at, and so I would like us to take a look of it again. I'd like us to have a look at it again. And so if y is given us exponential 3x, okay, so the solution that follows is that look at this function. It's a function of a function, because the function on its own is given as exponential x, and from your table the y dx is the same exponential x. Alright, when you get to higher levels you will understand why it remains exponential x, but this function is different because this has no variable, no coefficient, but this has a coefficient 3. Alright, so we'll treat this as a function of function, and so we have y exponential 3 where or you can say let's u be equal to 3x. Okay, and so we have y to be equal to exponential u. Alright, so that the y, the u will be equal to exponential u too, and then we differentiate 3x du with respect to x, and then we'll have 3, and so multiplying the two, you have du dx times dy du to give you equal to 3 exponential u. Alright, so that dy dx will be equal to 3, and exponential u will replace u as 3x. Alright, and with this it's goodbye to you till we meet in our next class.